Lastly, here we're going to look at logarithmic differentiation, which is very useful when we're trying to differentiate nasty-looking functions f of x, which are a combination of products and quotients and powers of easier functions. So the basic method is as follows. We take the natural logarithm of both sides of the equation y equals f of x, and we get the natural log of y on the left is equal to the natural log of f of x on the right. And we differentiate both sides with respect to x. So we're using implicit differentiation from calculus 1. On the left, we get the derivative with respect to x of the natural log of y is 1 over y times dy dx. And on the right-hand side, the natural log of f of x should break up into some linear sum of logarithms which are easy to differentiate. And lastly, we multiply the whole equation by y to get an expression for dy dx. Let's look at an example. Suppose I want to find the derivative of y equals x squared plus 1 over x squared minus 1 to the power of 1 over 4. Now, this is possible to do using a combination of the chain rule and the quotient rule from calculus 1, but it's a little messy. Let's apply the method. Step 1, we apply the natural logarithm to both sides. So we get the natural log of y is the natural log of this very messy function. And we can use the power rule and the quotient rule and the product rule for logarithms to break up the natural log of x squared plus 1 over x squared minus 1 to the 1 over 4 in this way. It's 1 over 4 times the natural log of x squared plus 1 minus the natural log of x squared minus 1. Now we differentiate both sides with respect to x. So on the left-hand side, as predicted, we get 1 over y times dy dx. And on the right-hand side, we get 1 over 4 times 1 over x squared plus 1 times the derivative of x squared plus 1 minus 1 over 4 times 1 over x squared minus 1 times the derivative of x squared minus 1. So you see the derivative of the right-hand side is quite easy to write down. It's x over 2 times x squared plus 1 minus x over 2 times x squared minus 1. Now we multiply both sides by y, and we get dy dx equals y times the right-hand side, and then we substitute our expression in terms of x for y to get dy dx equals the fourth root of x squared plus 1 over x squared minus 1 times what's inside the brackets, and we have an expression for dy dx. Here I've written a summary of what we've learned in this section. We've created this new function y equals the natural log of x. We've explored its graph. We've derived some rules for calculating with this new function, the algebra of logarithms. We have some new limits. The limit as x goes to infinity if the natural log of x is infinity, and the limit as x goes to 0 if the natural log of x is minus infinity. We extended the domain of this function to make a larger antiderivative for 1 over x, which applies for all x values not equal to 0, and with that we have some new rules of differentiation and integration. And in particular, we have this method of logarithmic differentiation, which we've explored in this last video.